Okay, so I mean this we could have written just by looking at this, that if I have a 90-degree pulse, Iz will go to minus Iy. In a very complicated way, we have got that answer. But we now know how to handle this equation of motion of the density matrix and how to calculate time evolution of the density matrix. At this point, I would like to pause for a second and see if there is any problem. Any questions from Duke or from anywhere else? Well, if
I have a question.
Yes, please.
If you write the sigma, I really miss the point. You take the trace over f. What does the f mean? Those are the free evaluation degrees of freedom, or what is it?
Can you speak a bit louder, please? I couldn't hear everything.
Yes, when you introduce the spin density matrix sigma,
Yeah.
on page 2.4, right?
3.
Right, you write sigma equals trace of f over rho. What does f means?
Okay, the trace. That's good. I skipped that. I had written down here. I thought it was okay. A trace of any operator means sum over all diagonal elements of that particular matrix. That is the trace.
Yes, but why did you put an index f here?
Why did I do that in?
Yes, there is trace f. This f is bothering me.
Oh, okay. When I go from rho to sigma, all right, that is to take the trace over all lattice variables, lattice parameters.
I see. Okay.
Yeah.
Okay.
And we then go from a global density matrix to a spin density matrix.
Yes. Okay.
Okay. All right. So now we are ready to calculate the time evolution of the spin density matrix in a two-dimensional NMR experiment. And we have these various periods: the preparation period, the evolution period, the mixing period, and the detection period. And we have the system at equilibrium before we start. So we have an equilibrium density matrix, and we apply a 90-degree pulse, a 90-degree pulse along y-axis. Then we get what we say is the density matrix at time t equal to 0. Please see the notation. This is equilibrium density matrix, and this is the density matrix at time t equal to 0, where my evolution period starts. So this is before sigma 0. Sigma subscript 0 is before the pulse. Sigma time t equal to 0 is after the pulse. And sigma 0 in the bracket is simply given by e to the power I pi by 2 Iy, sigma 0 e to the power I pi by 2 Iy. Okay. Somebody should have reminded me that this is R here. Okay. Because this is what I've done in the rotating frame.
I'm sorry, at Bowman Gray, we are looking at the people at Duke. We don't see you.
Sorry?
At Bowman Gray, we are looking at people at Duke, but we don't see you.
Do you see now?
No.
There is, the people who are handling the television, please repair the problem. Can you? Is it better now?
No.
Hello?
No. I can't see you.
You don't see me?
No, we got the image from Duke.
But you see the transparency?
No.
No.
Oh.
Pretend you're on radio and not TV.
Oh, you are on radio, not on TV.
Yes.
Oh. What can we do?
No problem. Yeah, I think there's a problem with that side at the moment. They're trying to work on it.
Oh, okay. I'm told that they're working on the problem, and pretty soon it will be corrected.
Okay.
but unfortunately today I have a rather large amount of material, and we will be cut off by these people at 5:30.
Now it's okay.
Okay, and therefore I will have to continue.
Okay, now we see you.
All right. Okay, wonderful.
I missed something. You have now
Oh.
Fy in the exponents rather than I at first line.
Okay, all right. I do that. Fy is equal to sum over I, y, I of each all the spins. And if I don't write this I here, I sometimes write it Iy. Okay, so this I should do it consistently as Fy. I often don't, and I may just write it as Iy. We will later on sometimes write as Iyk, which means spin k, and this is a notation. Okay, then we go back into the lab frame. No, I'm sorry, we are still in the rotating frame, but with the effective Hamiltonian H1, and then sigma 0. During evolution, our calculation of the density operator is at sigma T1 at this point is given by e to the minus I H1, which is the effective Hamiltonian during period T1, sigma 0 to the power I H1 T1. And this signal is a transfer signal, we know it, and it is decay by e to the power minus T1 by T2. And this I put phenomenologically into it. There is a component which is growing, because during this time, what I essentially had done was that I put my magnetization from z direction to the xy plane, and it is rotating, precessing, decaying in magnitude, but there is a component which is growing along the z-axis in time t1, and that growing component is given by this. The precessing component in the xy plane is given by this, and its decay is given by this component. Then the operation of the mixing pulse, period, I represent symbolically by operation r at the moment. And so at this point, my density matrix at T1 times 0, 0 is representing that T2 has not started yet, is given by r sigma T1 r inverse. What r is will depend on the experiment. Okay. And then during detection period, I have the sigma T1 0 here and T1 T2 here. This is given by e to the minus I H2 T2 sigma T1 0 e to the power I H2 T2, and it's decaying with T2 during T2 by capital T2, and there is a component which is growing also during T2. Okay, so the red terms are the relaxation terms, and the detected signal, for example, if I want to detect the x component or the y component, is simply given by the trace or that particular operator with the density matrix at time T1 and T2. And the constants I have written down here, but I'm going to drop them in the very next transparency. Okay, the peaks in two-dimensional spectra basically are of three types. There are peaks which are diagonal peaks, which have the same frequency in the two time domain. Then we have the cross peaks, which have one frequency in one time domain and another frequency in another time domain, which are the information bearing peaks. And we have these axial peaks which have zero frequency in time domain T1. And these are the peaks that come from this term. Okay, these are the zero frequency terms. If there is a zero frequency component present here, that will also contribute to axial peak. Okay, but these peaks basically are the ones which are growing during T1 with a zero frequency as from relaxation. And these axial peaks are not terribly interesting. They have some relaxation information, but it's easier to do that, get that relaxation information by one-dimensional NMR, and they can be cancelled away by co-addition of two different experiments. We will come to that later, but therefore they are not interesting. The term which is given by this red part does not contribute to signal, because when we take the trace with the operator x or y, it has no contribution. That means the growing signal during T2, small T2, during the detection period, this recovered signal is along z-axis. We are looking at xy plane, so this is not going to give anything, and therefore we can forget about that. So we are going to forget about this part. We are going to forget about this part, and so what we are left with is basically what I have in this equation on page 27. There is nothing I have done here except rewriting, combining all the things and rewriting the same thing. Okay, this is just the same what I have written before. In 4 different steps I have written down in 1 step. Okay, and taken a trace with the detection operator Fy. This was the starting density matrix. This was what happened during T1, small t1. This is the mixing operator. This is what happened during T2, and this is the detection operator. And the relaxation terms are given in red. Now, when we take the matrix element of this whole thing. All right, I should not have removed this. This was nice help. Let's take the matrix element. I want to take the matrix element of this whole business and take a trace. So I take the diagonal matrix element of this whole quantity. Okay, kk sum over k. And then I pull in the Fy here, and then I get KL because Fy is an operator which is not diagonal in the eigenbase, and so it may have off diagonal matrix elements. And then I have KL, LK of the remaining ones. Then I pull down the H2T out of it here, and H2T, since I'm looking at the eigenbase, and I must say that here, that the eigenbase of H1 and H2 are same. Most often H1 and H2 are same themselves, but they could be different. But if they have the same eigenbase, this is necessary. That means H1 and H2 must commute. Otherwise, they may not have the same eigenbase. All right. If they have the same eigenbase, then and in that particular eigenbase, this is diagonal, and so I have got HLL, and then RLM, and so on. And if I do this, it's basically I'm just writing FYKL, HLL, RLM, H1MM, sigma 0, Mn. That can be off diagonal, and then H1 and N, R inverse and K I have to write because I'm taking a trace, and therefore this is HKK, and these are the relaxation terms put phenomenologically. All right, so now I can collect the matrix elements, and we get 2 things. One is an amplitude, and the other is the frequencies. Okay, I collect the terms in the exponents having same small t1, and they collect the terms having same small t2, and so these are the frequencies, and this is the amplitude of the frequency. So what we basically get is that the result is that I have a time domain signal t1, t2, which has a frequency omega nm during time t1, which is decaying with a time constant t2, and has a frequency omega kl in time domain t2, which is decaying with a time constant t2, has an amplitude given by zklmn, and zklmn is a matrix element of this product of these 4 operators. Okay, and essentially pictorially this is what I have here, that you have a frequency omega kl in t2 and a frequency omega nm in t1 or omega 1, and this is omega 2 of an amplitude zklmn. So we now have an expression for the amplitude and the intensity of signal in 2-dimensional NMR spectrum, and where the amplitude is given by this. This is an additional paper that we have been given. It was not in the first one. I thought I'm going to repeat myself. I want to repeat myself once again. Okay. So what we have done is we have calculated the expectation value of the operator along y-axis. T1, T2 is given by trace Fy e to the power minus I h t2 r e to the power minus I h t1 sigma 0, and the unity transform of those. Symbolically, we sometimes write it like this, that I can write it sigma 0 here, and e to the power minus I h 2 hats on the h. But it's just a symbol, which means that I'm really writing this. Okay. Some people call it super operator, but that's all right. But we don't have to worry about it. Okay. At any time you see those two symbols, go back to your unity transform and write this up, and you will have no problem with this notation of super operator that you may encounter in a book or something. Okay. You may, of course, read all the algebra. That's all right. But if you don't want to, it's not necessary. All right. Similarly, I can write 2 hats on the R and 2 hats on the SH, and then I have a more compact way of writing the same thing, where sigma 0 is the initial state after preparation period. This is the frequency. This determines the frequencies in the T1 or omega 1 domain. This is the mixing operator. The frequency is in the T2 domain, and the detection operator. So basically, that's what you have to do. Okay. And this is, I summarize again. This is what we have done just now. Now we have the signal S T1 T2, amplitude ZKL, and I have dropped the relaxation terms from this momentarily. I think we will have to have them back after some time, but at the moment, just frequency KL in T2, frequency Mn in T1. And we have to Fourier transform this. We have the time domain signal, T1, which is function of time T1 and time T2, and we have to do a 2-dimensional Fourier transform on that.
Could you delay for a minute and go back to the apparently before and state again how you would define E raised to the minus I H with a double hat?
Okay. For me, it's just a notation. What it means is this, that e to the power I H double hat minus T operator
over.
R is equal to, for all practical purposes, e to the power minus I H T R e to the power I H T.
So that operation does this thing, right?
It's just a notation. Of course, it's a way of defining super operator. Super operator act on operators, and there's an algebra one can follow on that.
Is that the same operator called super operator? Is that the same called
Yes,
super operator and defined by
this
a
is the super operator.
commutator bracket?
Yes, it can be a commutator super operator, or it can be some other super operator. Yeah. This is here the commutator super operator.
You have made in the notes, you have made sort of 2 steps at once, because when you go to the next line, you have the double hat on the R as well.
Yeah. Oh yes, of course.
Yeah.
Then this R is just an operator, any operator, S, and then in that case, the remaining part is a operator, and then R acts on that, and then the R is also part of the operator on which the left hand side acts. So I can combine these into one operator. I can combine these into one operator, and then R acts on that. Then I can combine these into one operator, and this acts on that. Oh, sorry. Okay. Is that clear now?
That comes
So
about
the
just
arm with
because
double
these
hat-
operators these operators being exponential operators can in fact be applied in any sequence, as far as the operator is concerned.
The necessity of being an exponential operator, I'm not sure it's necessary to say that.
No, I don't think so. It does not mean that.
Yeah.
It is simply a notation. It's a shorthand notation. It's not the super operator because it still acts in a space of functions, not in space of operators. It's a simple way of using a shorthand notation for specific operation. It's nothing else, as far as I understand it.
As far as I understand, it is a super operator which is acting on the operator space,
It
and
is.
not on the function space.
Uh-huh.
Okay. Therefore, it's a super operator. Okay. All right. I mean, I really have written down at this point, as somebody pointed out from a remote site, that it is just a notation. If you have a problem agreeing to this, I don't have to write this equation forward. Okay, this is now, the rest is simple. Okay, then we have this time domain signal T1 and T2. We have written down, what we read down so far was a single detector signal, and maybe it is a real signal. We did not write a complex signal, but we will soon write a complex time domain signal. But let's just first use a single detected signal. We can call it a real part. And then we do a complex 2D Fourier transform on that, and we get a function which is a complex function, which is a function of two frequency variables, omega 1 and omega 2. And the two-dimensional Fourier transform is simply written as given in this term, which is a Fourier transform with respect to T1 and T2. The exponential e to the power I omega 1 T1 can be expressed as cos omega 1 T1 plus minus I sin omega 1 T1, and omega 2 T2 as cos omega 2 T2 and sin omega 2 T2. And then these follow each other, and therefore we have terms like cos omega 1 T1, cos omega 2 T2, minus sin omega 1 T1, sin omega 2 T2, and we have other terms like I times cos omega 1 T1, sin omega 2 T2, sin omega 1 T1, cos omega 2 T2. And I have just written down, you can call it cos and sine transform, you can call it real and imaginary transforms, and even I mixed them up. So soon you will see that I also mixed up in the next transparency. In any case, what we have then is the signal S, the frequency